Good day and welcome everyone. I'm the moderator, Dr. Umi from Institut SELFUEL, University Kebangsaan, Malaysia, which is the organizer of today's webinar. Our institute with the acronym SELFUEL was established in 2007 and headed by the current director, Prof. IR Dr. Siti Kartum Kamaluddin. SELFUEL is the first research institute in Malaysia focused on R&D works related to fuel cell and hydrogen energy. The institute began operation officially with the appointment of Prof. Dr. IR Dr. Wan Ramli Wan Daud as the founding director. The founding of this institute reflected the strength of research and development in renewable energy at the university, especially in hydrogen energy and fuel cells. At present, there are 7 research groups under the institute, investigating on various parts of the fuel cell and hydrogen technology, namely proton exchange membrane fuel cell, direct micro fuel cell, solid oxide fuel cell, biofuel cell, solar hydrogen, fuel cell processing, plant and material manufacturing, fuel cell electrochemistry, as well as in energy and policy management. Now, may I introduce you to our speaker? Prof. Dr. Nigel Brandon is Professor of Sustainable Development in Energy and Dean of the Faculty of Engineering at Imperial College London. His research interests are focused on fuel cells, hydrogen, and energy storage in support of the low-carbon energy transition. He is a founder and director of RFC Power, a flow battery company spun out from Imperial College in 2018. And the founder of Ceres Power, an alternative investment market listed fuel cell company, spun out of Imperial College in 2001, and which has a current market capital of over £2.5 billion. He has won awards in the field such as the Francis Bacon Medal from the American Society of Mechanical Engineers for work on fuel cell research and education, and the Silver Medal from Royal Academy of Engineering for contribution to fuel cell engineering, leading to commercial exploitation. He is a fellow Royal Academy of Engineering, a chartered engineer, fellow of the Energy Institute, and a fellow of the Institute of Materials, Minerals and Mining. He has recently joined SELFUEL for 12 months as a distinguished international professor. Please welcome our distinguished international professor, Dr. Nigel Brandon, for his talk titled The Role of Hydrogen and Fuel Cells in the Low Carbon Energy.
Okay. Well, good afternoon, everyone, and it's a pleasure to be here. Even if it's a virtual presentation, would have been very nice to be with you in person, but sadly that's still not possible. So it's a pleasure to be speaking to you from morning UK time, morning European time, afternoon Malaysian time. And I want to spend 40 minutes or so, half an hour to 40 minutes, talking around the role of hydrogen and the role of fuel cells in the low carbon energy transition. It's certainly a topic of increasing interest, which for those of us working in the space is very good to see. And we might just start off by reflecting why it's of increasing interest today. I'll show some links at the end, but thank you very much to my colleagues here in at UKM and in the SELFUEL Fuel Cell Institute for inviting me, for hosting me, and for organizing this webinar. And there's a link to their website at the end, but I'm also involved in 2 other programs. I'll provide a link at the end. One is the UK National Programme in Hydrogen and Fuel Cells, which we lead at Imperial College in London. And there's a link to that, and there's a website if you're interested. And the other is this Sustainable Gas Institute, a largely industry-funded research centre looking at all aspects around methane, natural gas, hydrogen, biogas, and so on. And again, there's a link to the website later. Okay, so I want to start by talking about drivers for hydrogen in the energy system. I've been working in this area for over 30 years now and have seen previous waves of enthusiasm for hydrogen and for fuel cells. I think this time it's different. I think it's more meaningful, and we can talk about why. I talked very briefly around the technologies that underpin this, what people refer to as the different colors of hydrogen, so gray or brown hydrogen, blue and green, what they mean. And just introduce again briefly the key hydrogen technologies. So that's carbon capture and storage and electrolyzers, 2 ways to make a low carbon or zero carbon hydrogen, assuming the electrolyzer runs on renewable power, and fuel cells as a highly efficient way of turning that hydrogen back into power. I'll then perhaps give an update on where we stand today on hydrogen for transport. Hydrogen for heat is much more of an issue here in Northern Europe than in Malaysia, but still you might look at hydrogen for cooling, but nonetheless here it's a big opportunity and challenge. The role of hydrogen as a system balancing vector, so the ability to store large amounts of energy for long periods of time and where that might have value. And then hydrogen for chemicals. And we need to, of course, remind ourselves that it's the hydrogen for chemicals and for the petrochemical sector in particular that's the main reason we make hydrogen today. And so how can we displace the hydrogen we currently make from fossil fuels with low carbon alternatives? Okay, so why the interest in hydrogen? And this is a figure, it comes from the UK, and of course every country is different, but it's the data I have, it's where I'm based. And this shows energy flows through the UK energy system over time. And the red line is energy flowing as electricity. The grey line in the middle is energy flowing as petroleum, so that's gasoline and diesel. And the blue wavy line is energy flowing as natural gas. And this shows some of the challenges in any energy system, in that if we want to completely decarbonize this energy flow, not only do we have to move all of the red line here to be low carbon by renewables or perhaps nuclear or carbon capture and storage, we need to use that electricity, or we need to replace anyway this grey line here, which is gasoline and diesel, with a low carbon alternative, which could well be electricity for electric vehicles or could be other energy carriers. And in the UK context, we have a particularly large flow of natural gas with big seasonal variations, because that's seasonal, that natural gas is used for heat. So in our winter months, as we are in at the moment, we have a much higher demand for natural gas than our summer months. And of course, to completely decarbonize the economy, we need to decarbonize all of these energy carriers, and we need to replace natural gas, which we cannot continue to use in an unabated form, with an alternative energy carrier. Now, electricity is obviously an option, and we can make more low carbon electricity, and we're making very good progress, and the world's making good progress on the whole in decarbonizing electricity. But you can see that we need to make an awful lot more electricity to displace these energy carriers. And also we need to be able to accommodate these very large differences in seasonal demand in places like the UK. And that's a really difficult and expensive thing to do with electricity alone. And so it's the opportunity for hydrogen to be an energy carrier alongside low carbon electricity, and particularly to manage some of these seasonal shifts and to think about its application in transport to replace some of this diesel and gasoline, and its ability to displace natural gas for heat, whether that's for space heating or for industrial heat, that's of interest. And it's that focus on a net zero energy transition that's really moved hydrogen back onto the agenda. It was certainly the case here in the UK that we, not that many years ago, had a commitment for an 80% cut in our CO2 emissions. And when we had that in place, all the really hard, all the really hard to abate sectors, like in some of the industrial applications or long distance transport, assumed they would be in the 20% that wasn't going to be decarbonized. Now there is a net zero commitment. There is nowhere, no sector of the economy that doesn't need to be decarbonized. And at that point again, the role of hydrogen in abating those hard to address sectors comes through. So I think all of these factors together are the motivation for the really marked increase in interest in hydrogen. And if we have hydrogen, then the most efficient way of turning that hydrogen back into power is in a fuel cell. And so it's also showing a marked interest, uptake in interest, excuse me, in fuel cells. Okay, more of that later. So carbon is a clear motivating factor and a clear driver, and decarbonisation is a clear driver for the interest in hydrogen and associated interests in fuel cells. This is a Knox map of London, and the red, the stronger the red, the higher the NOx levels. And those bright red NOx levels are really unhealthy levels. They are damaging to health. And this shows that the NOx levels track the main arterial roads in London. This is Heathrow Airport. These are the main roads flowing through London. And so we have very high levels of NOx emissions associated with transport use, with the combustion of fossil fuels in vehicles. And that obviously has health implications. So in many parts of the world, whilst carbon is an overarching driver, there are local drivers around air quality that hydrogen and its utilization in fuel cells, for example, which have very low levels of emissions of any, certainly no NOx emissions and very low particulate emissions, which bring associated health and air quality benefits at the point of use. So what might be the role of hydrogen in the economy? This is a figure comes from a paper we published, a sort of overview paper 3 years ago or 4 years ago now. And it paints a picture of the role that hydrogen can play. Hydrogen is helpful because it can be made from many different means and then used as an energy carrier. And once made, it's no carbon and low emissions. So we can make hydrogen from natural gas. That's methane here as the primary constituent of natural gas. We can do that today. It's done in steam methane reforming reactors. And if we capture the CO2 at the same time and put that into some form of sequestration or utilization step, that produces what we call blue hydrogen. So this is hydrogen made from fossil fuels, but with the CO2, most of the CO2 sequestered. So blue hydrogen is not zero carbon, but it is low carbon and much lower carbon than the hydrogen we make today without capturing the CO2. We can also make hydrogen from electricity by electrolysis, and assuming that those electrons come from wind or solar or some renewable resource, that gives us green hydrogen, in other words, zero carbon hydrogen that we can then put into the system. Once we've made the blue and green hydrogen, we can blend it together, mix it together, or use it as we wish. We can store it to provide some resilience to the system. We can take it and put it into a fuel cell. We can also take it and put it into a hydrogen turbine, as we would with a conventional fuel, and generate power. We combine it with CO2 if we've chosen to capture CO2, and we can produce methane or other synthetic fuels, so-called e-fuels, in which all e-fuels have hydrogen from electrolysis as an intermediate step. And of course, we can take that hydrogen into a whole range of end uses for buildings, for transport, or for industrial applications. So I think that the opportunity sits for or the question and the opportunity is around where would hydrogen best fit into a system alongside low carbon electricity as the other main energy carrier. So we make hydrogen today. We make hydrogen from fossil fuels. About 96% of the world's hydrogen is produced from fossil fuels. We use 6% of the world's natural gas, 2% of the world's coal to make hydrogen today. But of course, we don't make it as an energy carrier. We're not making that hydrogen to go into other parts of the system. We're making it for the chemicals industry, for fuel upgrading and hydrogenation reactions and so on. So we need to make a lot more hydrogen if we're going to use it to displace for transport fuels and for heat. And then we come into these new modes of making hydrogen, either blue or green. And that's where a lot of the interest is today. In many parts of the world, green is the hydrogen of interest. In some parts of the world, blue is of interest as well. So just one slide on carbon capture and storage. And this is a typical scheme for a carbon capture and storage plant in which we're gasifying, in this case, coal. We're going through a shift process to take that those gases, those CO2 and hydrogen-rich gases, and moving them into a more concentrated hydrogen and CO2 stream. We can then capture the CO2, separate and store the CO2, and then take the hydrogen either into a combined cycle plant, as shown here, or it could be used for all those other applications that we've just spoken about. And anyone interested in learning more is welcome to look at our Sustainable Gas Institute report on carbon capture and storage. But today I want to focus on the electrochemical technologies, fuel cells, and to some extent electrolyzers. There are, broadly speaking, 3 types of electrolyzer. 2 of these are widely available commercially. So alkaline electrolysis and PEM electrolyzers. Alkaline electrolysis has been around for a long, long time, well over 100 years. It's well established and a mature technology. It has a relatively large footprint. They're quite big pieces of equipment, but they are available at large scale from a global supply chain. Efficiencies today around 65% or so for taking power into hydrogen. They're not particularly flexible. They were never designed to directly connect to renewable generation or demand. So that has some, they're more of a base load hydrogen generator, but they are the lowest cost electrolyzer technology today. PEM electrolyzers are relatively new, but are now increasingly available. They have the advantage, they have the advantage over alkaline in that they're more flexible, they can load follow better, they can produce hydrogen at higher pressures, which has a number of advantages, particularly for vehicle refueling. But they have the disadvantage that they have platinum group metals in them, particularly iridium, which is a concern if we're going to make these in large volumes, and also platinum. So they are more expensive, they have higher cost materials, but they can produce, as I say, high pressure hydrogen. So particularly for vehicle refueling, these are the sorts of electrolyzers that are commonly used. And then a newish variant, certainly not yet commercially mature, which is solid oxide electrolysis. In solid oxide electrolysis, this runs at high temperatures. In fact, the hotter the better for high temperature electrolysis, whereas these devices are low temperature, they run at under 100 degrees C. This is running up at about 800 degrees C or so. And high temperature electrolysis is much more efficient than low temperature electrolysis, whereas these technologies are about 65% efficient. This technology can get you over 90% efficient. Today, there's only one company that will sell a solid oxide electrolyzer, and that's a company called Sunfire in Germany. But lots of the solid oxide developers are now have now got programs to develop high temperature electrolysis. Disadvantages, well, it's not as flexible as you would expect with a PEM, but it is significantly more efficient. And at the moment, we still need to develop the maturity. As I say, there's only one supplier, and they will sell you a 150 kilowatt unit, whereas you can buy megawatt units of PEM electrolyzers and hundreds of megawatt units of alkaline. So a journey to go, but the efficiency probably worth pursuing. What about the cost of hydrogen, right? And this is a big factor, and it's a very real issue. This data comes from the recent report from IRENA, the Renewable Energy Agency, I think is a nice report if you're interested in looking at green hydrogen. I've had no association with it, but it's very comprehensive. And they paint a picture of green hydrogen cost reduction pathways. It's certainly the case that today green hydrogen is the most expensive form of hydrogen. 60 to 80% of the cost of green hydrogen is the cost of the electricity. So future cost down is very sensitive to electricity cost, and particularly therefore renewable electricity cost. And this is this block here, electricity cost. This is a prediction of where prices will go, or forecast, if you like, of where prices will go. And this shows the impact of roughly halving the electricity price, roughly halves the, not quite, but almost halves the cost. Electrolyzer costs themselves, an 80% reduction in electrolyzer cost doesn't make that much of a difference, right? It helps, but the big difference is the electricity cost. Electricity efficiency makes a big difference because, of course, it's directly coupled to the cost of the electricity. And this is why the high temperature electrolyzers might be of interest in some areas, because that efficiency gain is significant. And then there are further incremental improvements in cost associated with the amount of time the electrolyzer runs, some issues around lifetime, and risk, which affects the cost of borrowing money. So the IRENA paint a picture in which we can get our green hydrogen price points down to $1 a kilo. And at that point, you've really got a cost-effective option. So that's the sort of flight path to green hydrogen cost reduction. And many commentators view green hydrogen becoming cheaper than blue by about 2030. And in some parts of the world, for example, with very low cost renewables today, green hydrogen will be very cost effective much earlier than that. This work from IRENA is consistent with some of our own analysis. This is some work we've done in the UK for the Committee on Climate Change. And again, without going into it, this is a 2030 vision of the cost of green hydrogen now in pounds per kilo. So £2 a kilo is about $3 a kilo by 2030. So it's a consistent view with the grey bar here showing the proportion of that cost. That's the cost of the electricity, which again is forecast and shown here to be significant, and the blue being the cost of the electrolyzer. and a vision of how that might continue to fall out to 2050, sensitive to things like the electricity price and the electrolyzer efficiency. So it's a consistent vision. So I've mentioned fuel cells already. Just sort of a quick introduction to fuel cells, and obviously the SELFUEL is a fuel cell institute. The great attraction of a fuel cell is it's the most efficient way to turn a fuel into power that we know. And it's a very efficient power generator that is efficient down to quite small scales. And that's another valuable attribute, particularly for sort of highly distributed or more distributed applications. There are a range of different fuel cell technologies. I haven't shown them all on here. They include direct methanol fuel cells. And if you were watching the the SELFUEL video earlier, you see that's an area of activity in the group. But I'm focusing here, and there are molten carbonate fuel cells, which are less well developed these days. But I'm focusing here on what we might consider the two main industrial applications today: polymer fuel cells, or proton exchange, or polymer electrolyte membrane fuel cells, PEMs, and solid oxide fuel cells. So let's look at the PEM side first. In a polymer fuel cell, we put hydrogen as the fuel on one side of a membrane. The membrane is an ion conducting membrane. It will conduct only protons. And on the other electrode, or on the other side of the fuel cell, we pass oxygen in the form of air. By having the fuel and the air physically separated, it allows us to harvest the electrons that are transferred in these redox reactions. So on the anode, that's the hydrogen side, we have a reaction where the hydrogen molecules will release protons and produce electrons. If these electrons are allowed to pass around an external circuit from one side of the fuel cell, the hydrogen side, to the air side, then they will combine with oxygen on the air side and produce water. So the overall reaction is hydrogen plus oxygen goes to water, but we're capturing the electrons that are transported in that process, and that flow of electrons is heat. Sorry, that flow of electrons is electricity, sorry, and the voltage is generated associated with the thermodynamic driving force for the reaction, specifically that gives energy. So a fuel cell will generate perhaps around 1 volt when currents are very low. And as we draw more current, the voltage will fall, but the power will go up. And so voltage times current is power, of course. So in this way, we generate electricity very efficiently. We're harvesting those electrons directly. We're not going through a combustion step. And that gives us a very high electrical efficiency. So even a small fuel cell of 1 kilowatt or so running on hydrogen can be well over 65% to 70% even efficient. And that efficiency is retained as we go up to larger units. So that is an interesting characteristic. It gives us a very high efficiency. You can see the only reaction products is water, and there are no combustion steps to generate NOx or particulates. Now, this type of fuel cell runs at about 80 to 100 degrees centigrade. It has an ion conducting membrane here, which is a material that needs to be kept hydrated. So we have to think about water management. We produce water here, so there's plenty of water around. But we can get dehydration on this side from the protons transporting water across. And we can get too much water causing flooding on this side. So water management we have to manage to keep the device working effectively. And the anodes and cathodes have platinum group metal catalysts in to catalyze these electrochemical reactions. That introduces some cost, but these days there's been huge progress on thrifting out the platinum. And now that's not, whilst it's something we need to be aware of, it's not a major cost driver for fuel cell, PEM fuel cell technology. On the high temperature side, so solid oxide fuel cell, and we'll talk more about these in a little while, these are devices that have a similar principle. Again, we're putting hydrogen or a hydrogen-rich gas onto the anode. We're putting oxygen in the form of air onto the cathode. But now, instead of transporting protons across the membrane, we're now transporting oxide ions across the membrane. So our oxide ions are going from the air side to the fuel side. The overall principle is the same. We're releasing electrons on the hydrogen side. We're consuming them on the air side, the cathode, and that's producing our oxide ion. So the overall reaction is the same, except now our reaction product, which is water, or at the operating temperature, these devices steam, is produced in with the fuel, whereas on the PEM it's produced in with the air. These devices work somewhere between 600 and 900 degrees centigrade. They have to be hot to get you the ability to conduct the oxide ions through the ceramic materials that are used here. So these are ceramic devices. They're hot, so they don't need precious metal catalysts. They use more base metal catalysts on the anode and the cathode, things like nickel and cobalt and various doped perovskites, manganites, and so on the cathode side, and normally nickel and a mixture with the electrolyte on the anode side. So the different principle, different characteristics, and produce high-grade waste heat because, of course, they also produce steam. So in general, historically, solid oxide fuel cells have been focused on stationary applications and PEM fuel cells on transport applications, but you will see applications of PEM in stationary and solid oxide in transport. Okay, so having talked in general terms about the different technologies, let's go on to look at some of this current status and where things are today. So let's talk about hydrogen for transport. If I look back to the sort of 1990s and the year 2000s, when there was a wave of enthusiasm for hydrogen fuel cells, the focus was really all around light-duty transport, with the primary focus being around hydrogen fuel cell cars. At the time, the technology wasn't really mature enough, and the world didn't really need a hydrogen fuel cell car. So coupled with those two things together, in fact, interest waned. To the point at which actually there was probably a negative pushback on hydrogen fuel cell technology, which we're now recovering from. Over the rest of the next 20 years, quite a few developers and innovators fell away, but a number of companies stayed the course. And particular highlight here the work of Toyota and Hyundai, who've both persevered with hydrogen fuel cell technology for automotive applications, and have both got products on the market now in relatively limited numbers, but commercially available. This is our Toyota Mirai that we have at my university, thanks to support from Toyota. It's a very nice car to drive, and I do use it fairly often, and we use it as a fleet vehicle on the university campus and to drive between different locations. So this Mirai will cost you quite a lot of money. It's £50,000 for the new Mirai. That's quite an expensive car, and it's certainly quite an expensive Toyota. But nonetheless, it will do 400 miles. This particular one does about just over 300 miles, but the new one will go a little bit further. The biggest disadvantage when I drive this car is that there aren't many places in London where I can refuel it. In fact, there are only 5 or 6 different hydrogen refueling stations in and around London. So it's still the case today that it's quite a difficult choice for a consumer to want to buy this car, and most of these vehicles today are owned either by very early adopters or taxi hire firms that are offering a green transport solution. But that aside, it's a very convenient car to drive. It's an electric car. You can refuel it in just a few minutes, and it will go 300 to 350 miles. Hyundai brought out their new fuel cell electric vehicle, the Nexo. This is a more expensive vehicle. I have yet to drive it, but again, it's very well regarded in terms of a hydrogen fuel cell vehicle. I think the main challenge for hydrogen fuel cell light duty transport is it goes head to head at the moment with battery electric transport. All of these vehicles are in fact a fuel cell battery hybrid. They all have a battery in them. This Toyota Mirai actually takes a lot of its technology from the Prius hybrid vehicle technology that Toyota developed for the Prius. So it has a nickel metal hydride battery in it. It's got very similar sorts of approach to that, but it replaces the internal combustion engine with a fuel cell. But really going head to head with battery electric, and it's not so obvious to me at the moment, we can discuss it, that hydrogen fuel cell electric will win over battery electric in the light duty market, mainly because of this hydrogen refueling infrastructure. I think as a vehicle, they're a very practical choice, but it's a question around how we put in these hydrogen refueling stations. They are going in, but still the numbers are not such that as a consumer, it's an obvious choice to buy a hydrogen fuel cell car today. Where I do think there's a lot of opportunity for hydrogen fuel cells in the nearer term is in larger vehicles. Buses is a very good example. As the vehicle gets larger, the energy demand goes up. It's not so clear that the battery electric option can compete and provide a practical solution for large energy requirement vehicles, either because they have to drive a long way or because they're very heavy. So buses, I think, is a really interesting opportunity. We are seeing increasing interest in hydrogen fuel cell buses. Obviously, they operate in urban contexts where air quality matters. They often have a social benefit associated with them as a public transport mechanism. You can operate your bus from one depot. You only need one refueling point to service your bus fleet. And they do a fixed duty cycle, which is well understood and defined. So there are lots of opportunities for hydrogen fuel cell buses, and we're seeing increasing interest there, particularly in Asia, but also in Europe and North America. I think the other market that's really picking up in terms of its interest in hydrogen fuel cell technology is the truck market. Again, trucks are not well served by pure battery solutions. We need to replace diesel and petroleum fuels in truck use. There are not many options to do that. Really now, I think the fuel cell hydrogen option is competing against synthetic e-fuels or biofuels with internal combustion engines, not so much against batteries. And there's a lot of interest now in truck developments for both kind of smaller trucks up to very large vehicles, with some serious companies and players coming to the table in the truck market. This is an application area I hadn't really foreseen, perhaps 10 years ago, which is hydrogen fuel cell electric trains. Again, as we seek to decarbonize all aspects of the economy, where we currently use diesel electric trains on particularly suburban lines, it's quite expensive to electrify those lines. They don't take the transport passenger numbers to justify the capital expense. And so increasing interest in hydrogen fuel cell electric versions of those trains now. They've been running in service in Germany for quite some time now. We've now got one over in the UK as a prototype trial. And they allow the train operator to produce a low carbon variant, or a zero carbon variant, without the cost, all the upfront capital cost of electrification. Again, the train runs from a fixed point, so the vehicle refueling is much simpler. So lots happening on the transport side, but really focusing on where hydrogen fuel cells are advantaged. So the heavy duty, long distance applications. I haven't put marine on there, but that's another area that's of potential interest for hydrogen, and even sort of transatlantic ocean shipping, if not on hydrogen, then on green ammonia, which you make from green hydrogen. Now this next couple of examples are for places that need heat. Perhaps that's less relevant in Malaysia. But in some countries, and the UK is one, we use a lot of natural gas for heat. And if anyone's interested in this broader issues, we did produce a report on this from our Sustainable Gas Institute and some associated papers. But the figure on the left here shows the percentage of households, so where people live, connected to the natural gas network. And the highest interconnectivity is in the Netherlands, and the UK is second, where 85% of people where we live is connected to the gas network, and we rely on that gas for heat. We also often rely on it for cooking. But you see there are other countries with high levels of natural gas penetration into the building sector. In a zero carbon world, we can't continue to do this. So this is a big difficulty and a big challenge for the countries that are very reliant on natural gas today for these heat applications. So one of the opportunities here is to think about, obviously, hydrogen to replace natural gas, but also once that hydrogen's coming into the home, to think about putting a fuel cell into the home to take that fuel and turn it into heat and power. Now, Japan has been one of the leading exponents of this. This is a vision of a Japanese home of the future, with its fuel cell micro CHP unit. So the micro CHP unit means it produces both heat and power. Obviously renewables embedded into the building as well, and then energy efficiency and sort of energy demand reduction measures integrated into that. Over 300,000 fuel cell micro CHP units have been sold to consumers in Japan, not operating on hydrogen. They're operating on natural gas or LPG. And the right sort of technology can do that today. So particularly the higher temperature fuel cell technology, and then switch to hydrogen in the future when hydrogen is ready. And so that's a really interesting opportunity. Just tell you a little bit about some of our own work in this area. Was kindly mentioned in the introduction. 20 years ago, we set a company up called Ceres Power, now known as Ceres, based upon some of the work we've done on solid oxide fuel cells. It's a company targeting solid oxide fuel cells for a range of applications using a unique particular approach that uses a metal support rather than a ceramic support, which makes a more robust technology. All the slides here are taken from their annual general meeting, which was in December. And you can see where interest in these, not just Ceres is, but all companies working in hydrogen and fuel cells today. Its market cap in December was 1.8 billion. Its market cap, well, yesterday anyway, was 2.5 billion. So huge growth in their interest and value in all companies active in this space, including Ceres. So Ceres have developed this. This is a metal supported solid oxide fuel cell. It's a ferritic steel that's stamped, cut, and then the fuel cell layers are coated onto this region here, and then stacked to make a unit of a few kilowatts or so. And then those units go inside various products. These products are developed by others. So Ceres produced this bit, the fuel cell and the associated hot box, as it's called. And you can see the commercial partnerships with Bosch, for example, have taken a 20% stake in the business, and a manufacturing facility is being built in Germany at the moment. The products are available in Japan now. This is a 4.2 kilowatt micro CHP unit aimed at Japanese, small Japanese retail units and offices. You can run it on natural gas today, and you can switch it to run on hydrogen tomorrow with no change. Weichai Power in China are putting these units into buses. So again, this is a transport application of a high temperature fuel cell, and a partnership with Doosan to make larger scale units in South Korea. So the world is actually waking up to fuel cell opportunities now, and there is a market. In 2019, 1 gigawatt of fuel cells were sold globally. Obviously, Ceres only played a very small part in that. So there's a lot of activity and commercial rollout starting of fuel cell technology. And again, here you can see the key partnerships that the company has. So it shows the flexibility of fuel cell technology and the range of applications that they can be pursued in. All right, so just another couple of areas to talk about in my last few minutes of my presentation. I want to talk about hydrogen for system balancing. So why do we talk about hydrogen for system balancing? So this slide here comes from my colleague, Goran Strabak, who's a power systems engineer and economist. And it makes a couple of points that I'll talk to. Firstly, as we put more and more renewables into the system, so this analysis is for the UK, and the UK is an island. It doesn't have strong interconnections, and therefore it's more sensitive to some of these issues. The UK will rely on wind as its primary renewable. We actually have the best wind resource in Europe. And as we put more and more wind into the system, this is in gigawatts, the percentage of wind curtailed goes up. So that means that we have to not take power from the wind farms, because there are going to be more times when the electricity system doesn't have the capacity to receive that power. And this inability, or if you like, the cost of upgrading electricity systems to be able to accept more and more renewables is a huge factor in some of the cost points for increasing renewables penetration. So that's one way of looking at it, right? So we curtail the wind, and therefore we're obviously not getting value from that in renewable investment. The other way of looking at it is to say, well, what we'll do is we'll build let's assume there are no constraints, and we'll build a big enough electricity system to receive the peak power. And again, when we do that, and over time, as the renewables penetration increases, we have to put bigger and bigger amounts, the capacity, the peak power capacity of the network has to go up, but the amount of energy it's carrying doesn't significantly go up. So the utilization of that asset goes down. That means we're spending a lot of capital, which we're using less, and therefore the relative cost of that capital becomes more and more significant. So this becomes a very expensive option as well. So either we're this is expensive because we're not using the renewables we've invested in, and this option is expensive because we're not utilizing all of that infrastructure investment efficiently. So if we can find a better way to do this, either through, for example, flexible technologies that can balance supply and demand better, then in the UK economy, that's worth about £8 billion a year. So that's your saving that's available to invest in technologies that deliver you that. And this is where things like batteries and also flexible generators like fuel cells come in. The other big, if you like, strategic issue, and again, I can speak to Northern Europe on this, was that if we go with high levels of wind to generate our power, unfortunately, in the middle of winter, about now, usually in Northern Europe, we have a period of several weeks where the wind does not blow. And if the wind does not blow, we will not generate any wind power, and then we will not have any electricity. And if we're relying on that electricity for things like heat, at a period of peak heat demand, that clearly is not a sustainable, not a resilient solution. One option is to store energy as a molecule, and of course we do that with natural gas today. We have strategic reserves of natural gas. We also have a global trade in LNG. And this is, again, an estimate from my colleague, that for the UK, if we had 4 weeks of no wind, we'd need somewhere around 20 to 40 terawatt hours. If we had 2 weeks of no wind, we'd need about 20 terawatt hours of stored energy. And for those who don't have a sense of these things, 20 terawatt hours is about 1,000 very large pumped hydro facilities, which we've only got one in the UK, and we couldn't build probably another one, let alone 1,000, because we just don't have the right geography for it. So you need to find another option, and one option is to store that energy as hydrogen. We already store hydrogen in underground caverns. We certainly store lots of natural gas that way, but we also store hydrogen. Solution mine salt in particular types of salt reserves and salt caverns to produce the hydrogen stores. It's done for different purposes in the petrochemicals industry, for example. And the largest store in the US would hold 100 gigawatt hours of hydrogen. So again, not a terawatt hour, but getting on for it. At least it's closer than the pumped hydro. Sorry for the low resolution, but this was a figure I grabbed from a recent paper from the International Journal of Hydrogen Energy, a German study actually looking at the potential of salt caverns for hydrogen storage in Europe. And this is cavern storage capacity in terawatt hours, and this is 1,000 here. This is 1,000 terawatt hours, and if you might remember here, we need about 10 terawatt hours. So we need right down here. So there's no country in Europe pretty much that doesn't have the capacity to store hydrogen in salt caverns of the right amount, if that's what we needed to do. So that's a really interesting option in a true net zero economy. And then finally, just to touch on some of our most recent spin out, which is hydrogen related, but is a flow battery. Again, it's in the energy storage space, and it's about technologies that deliver flexibility to the system. So in a flow battery, you store energy typically with redox couples in 2 different tanks. What we've invented here is a technology that has a manganese redox couple in this tank and then uses hydrogen in a closed loop on the other electrode. And when you want to store energy in the device, you make hydrogen, effectively electrolyzer mode on this side of the flow cell or reversible fuel cell, and you generate the oxidized form of the manganese redox couple on this side. You store it in a tank, and you store it as a few bar of hydrogen in a closed loop on the hydrogen side. And when you want power, you put the hydrogen back through. It runs in fuel cell mode, and now you put the oxidized form of manganese in, and it's reduced, so it acts as a fuel cell. And this gives you much lower energy storage costs than you can achieve with lithium-ion batteries for longer term energy storage. So for storage of above about 4 hours in duration, this becomes cost effective relative to lithium-ion. And once you're at about 10 to 12 hours duration, which is just the sort of duration increasingly needed to back up photovoltaics, then you're much more cost effective, well below $100 a kilowatt hour. So that's the technology we're pursuing at the moment, and we have a small company taking that forward. But again, it's an electrochemical cell that sits at the heart of that. So my last couple of slides then are around the chemical sector. As I say, this is how we make hydrogen today, or sorry, the areas in which we make hydrogen today. Slightly wordy slides, for which I apologize. But things like ammonia, for example, represent over 1.4% of global CO2 emissions, and we use a lot of hydrogen for making ammonia. As I say, we make hydrogen from gas and coal today, and that gives us quite high intensity ammonia, as well as quite high intensity hydrogen. And the issue about green ammonia as well as green hydrogen is therefore of interest. And just some examples of where things are. So even during the pandemic and lockdown in 2020, we've seen big projects come on board. So a 100 megawatt electrolyzer plant in the chemical sector for making green methanol. Shell's work on the green hydrogen hub in Rotterdam using wind power to help decarbonize existing refinery plant. The world's largest green hydrogen project, at least at that time, unveiled in the middle of last year in Saudi Arabia. So 4 gigawatts of renewables going in to make green hydrogen, and that green hydrogen converted to green ammonia and then exported. And we've just seen, late last year, there was an announcement of the Asian Renewable Energy Hub in Australia, which is an even larger project to take renewable power in Australia to green hydrogen and green ammonia, and then export that green ammonia. So really interesting time in the space. So some web links here. If anyone wants any further information either on the Fuel Cell Institute at UKM, the work we do at Imperial in the Hydrogen Fuel Cells Hub and the Sustainable Gas Institute, our broader energy program in the Energy Futures Lab. And we also run a consultancy in this space if anyone has interest in following up on any technological or commercial work. Okay, I'll stop there. Thank you very much indeed. I'm happy to take any questions you might have. And
thank you, distinguished international Professor Dr. Nigel Brandon, for that impactful talk. We'll now start our Q&A session. We've received quite a lot of questions, so we'll see how we'll arrange the time for the Q&A session. So the first question comes from Tan Sri Abdul Wahid, Chairman of the UKM Board of Directors. His question is, thanks Prof. Brandon for a very informative presentation. I understand 1 kilogram of hydrogen will provide a range of 100 kilometers, and each kilogram costs about $6 US. So the cost per kilometer is about 6 cents. How workable can refueling be done in canisters of 1 kilogram or 2 kilogram each to overcome the constraints of hydrogen refueling stations?
okay, so yes, I guess the question is, could you have so at the moment, that hydrogen is stored on those vehicles as high pressure. It's 700 bar compressed hydrogen, so that's very high pressure hydrogen. It has to be injected using obviously a specialist refueling point, but it is available and designed for ordinary customers to use. Having used one a number of times, it's not unlike using a petrol station. You take a nozzle, but as unlike in a liquid fuel, which you hold the nozzle in the petrol tank, in this case, you effectively lock the nozzle by turning it and rotating it and clicking it into the same place as the filler cap on a car. It's just now going to be a hydrogen filler cap. And then you press a button on the refueling system and it generates the pressure and balances the pressures. It takes a couple of minutes. So could you have a different way of moving that hydrogen around? There's a lot of people interested, and there's been a lot of work on alternative hydrogen carriers. Obviously, you can't really have a small amount of high pressure hydrogen. That would be quite a hazardous thing to do. But you could think about other hydrogen carriers, methanol is a hydrogen carrier. And could you take that liquid methanol and extract the hydrogen through a thermal process on board the vehicle? Or alternative hydrogen carriers, various hydrides have been considered, which again, you can heat up and release hydrogen from them. Various chemicals like lithium borohydride have been considered. In practice, they all work quite well for very small systems, but they become very expensive for larger systems. And there is also a question around the reversibility of some of those carriers as to the amount of energy you need to put back in to make them regenerate the carrier. So at the moment, there isn't a successful alternative to high pressure hydrogen. The buses and sort of truck applications tend to use more like 350 bar than 700 bar. That makes the hydrogen storage much cheaper. And indeed on that Toyota Mirai, the most expensive part of that car are the hydrogen tanks that you use to store the hydrogen in. So it's a really interesting idea. If you look at drones and things like that, they tend to, that's where you see more the hydrogen carrier, sort of hydrogen cartridge idea, where you pop in a cartridge of a carrier and then generate the hydrogen and then take the cartridge out and swap it out. We've not seen it being successful as yet for larger vehicle applications.
Okay, thank you. So the second question is from Dr. Nurazwan Ashari, KM. In terms of engineering and sustainability, what are the main challenges and issues in developing hydrogen economies?
Okay, well, there are many challenges, right? So, as I've said, I think we need to think about, we need to be quite more nuanced or more targeted, call it what you will, in thinking about where we're going to use hydrogen and where is it advantaged. So I come to the kind of, as always, you've got to start somewhere. So I would suggest that in the transport side, starting around buses or heavy duty vehicles, vehicles that you use for road sweeping, vehicles you use for refuse collection, again, where there's often owned by a local government, say, who might see a public benefit in early adoption of some of these technologies, is a good place to start. You don't want to have to start with putting in place a national hydrogen infrastructure, because that's going to be expensive. All of the work that I've seen on how you roll a hydrogen infrastructure out nationally says you start with kind of point opportunities where you can generate hydrogen. Obviously, you've got to be able to generate that hydrogen, and your choice there depends a bit on your vision for the country that you're in. Do you want to go with green hydrogen from electrolysis? Well, that's okay if you've got a lot of renewable power. Do you want to make it from fossil fuels? In which case you've got to think about it won't be zero carbon, but it'll be low carbon. But if you've got a lot of fossil fuels, that may make sense to you as a country. Do you want to make it from biomass? If we make it from biomass, again, Malaysia is an interesting case in point, right? Where we may make large amounts of hydrogen from biomass. We make it from biomass with carbon capture, in which case we've got negative CO2 emissions. And perhaps there's then a market for selling those negative emissions in one country to another country. So you can get also a credit for those negative emissions that provides an additional revenue stream. So the choices vary a bit depending where you are and how you do it. But you've got to have obviously a source of hydrogen. You've got to be able to make that hydrogen. You've got to be able to get it to where you need it. And I think you kind of bootstrap applications up together like that. If you try and assume that you'll end up with a national, well, start with a national infrastructure, I think that's too expensive and probably too difficult. So, I mean, those are the specific. Well, those are perhaps some of the things to be thinking about. So, if you're thinking about a hydrogen strategy for Malaysia or for other countries in the region, these are the sorts of things to be having in mind, I think, as well as then what technologies you've got locally that you might want to promote and develop.
Thank you, Prof. The next question is from Mr. Gurmesh Singh Sidhu. Dear Prof, what are the initiatives that have been taken till date to find a flexible utilization for reduction of cost and decreased redundancy of usage versus time in the hydrogen system balancing grid lines?
Sorry, say that last point again. What's been, say it again.
what are the initiatives that has been taken till date to find a flexible utilization for reduction of cost and decreased redundancy of usage in time?
Yeah, well, I mean, we have to, remember that at the moment, we don't have a lot of this conversation and excitement is still predicated off the back of what we're going to do rather than what we've done. So if we look at what hydrogen projects are around, they're largely projects, right? There are particular demonstration projects or activities. I mean, there are hydrogen buses and there are hydrogen trains, and that's great, but they tend to be project-based rather than national infrastructure-based today. So this is all around where costs will go going forward. As I say, the cost of green hydrogen is very sensitive to the cost of renewable power. So those two things are directly coupled. And that's why you're seeing that project in Saudi Arabia, where you can make renewable electricity at 1 to 2 cents a kilowatt hour. And that makes very low cost green hydrogen. But you've then got to move it from the middle of the desert in Saudi Arabia to somewhere where we actually need it. And obviously that adds extra cost to the process, which is where the green ammonia piece comes in. I think the other thing is on electrolyzer capacity. Again, we need to remember that today we make electrolyzers, but we don't make electrolyzers at the scale the world's going to need. And if you look at the national commitments around electrolysis rollout from countries that have made it, with many gigawatts of capacity promised, that is many times more the amount that we can make at the moment. So we have to scale up manufacturing. We've just seen the UK actually has the world's first gigafactory for electrolyzers announced. There's another gigafactory in the US just been announced. We're starting to see very large companies like Cummins and Siemens investing in the space. And that's key, of course, because without those sorts of companies involved, we won't get to the manufacturing volumes we need to drive down price. And indeed, the manufacturing volumes we need to install a global capacity of many gigawatts. So those are really interesting points. On the fuel cell side, we haven't quite seen that level of investment yet. So I think fuel cells is lagging behind a little bit on the electrolyzer excitement at the moment, but it's really coming through. Series are now up to about 0.5 gigawatt annual production. So my own view is that if we look at what's happened with lithium-ion batteries, costs really tumbled once we hit gigawatt scale. And I think the same thing will happen with these other technologies. And we're not quite there in fuel cells, but we're getting there, and we are just arriving there in electrolyzers. And that will make a big difference to the cost point and the supply chain. And at the moment, there's a lot of it's supply chain issues. It's less R&D and it's more manufacturing rollout, scale up, and installation and things like that.
Thank you, Prof. So the next question is, in a post-COVID recovery environment, what are your views for countries that intend to focus on creating high-skilled hydrogen and fuel cells related jobs in sectors that will be critical to the future economy, such as low carbon energy, transport, and heavy industry?
Well, I think it's certainly a very rational idea, right? Which is to think how countries should be thinking about where they're advantaged. Again, if I look at the national so those countries that have issued national strategies for hydrogen, and there's quite a lot of them in the last couple of years. If you look at countries like Spain and Portugal, so southern European countries with high levels of solar and wind renewable potential, their hydrogen strategies are very much around how can we become an energy exporter? How can we utilize our renewables and market those, in their case, probably to Northern Europe, right? Because that's close, where we don't have as much renewables or don't have as well cost advantage renewables. Can we become an exporter can we become an energy exporter, right? So it offers countries that are not traditionally fossil fuel exporters the opportunity to become energy exporters. It'll all be cost driven. It also offers countries, of course, with particular technology capability. So the UK happens to be very strong in fuel cell and electrolyzer technology, so that's good. We're very keen to develop that and retain that advantage. If you look back historically, the lithium-ion battery was invented in the UK at the University of Oxford by John Goodenough. And at a time when there was no interest in these sorts of high-tech things in the UK, and it was licensed and sold to the Japanese, and that's that. We don't want to do that again. And you'll find similar examples in other countries. Obviously, in the transport sector, you've got, I mean, the UK makes most of Europe, all of Ford's engines for Europe are made in the UK, right? If we're not going to have internal combustion engines anymore, what happens to all of those jobs? Germany, of course, is very concerned. It's very reliant and has a very big automotive industry. They've invested heavily in battery EVs for that reason. If we're going to look at companies like Volvo on trucking, so all of these present opportunities and challenges for incumbents. They are challenges for incumbents and opportunities for others. And we've seen what's happened with Tesla, right, on battery EVs and how that's driven what's happening in light duty electric. So there are lots of things, any disruption presents opportunities and challenges. And I think if you sit passively wait, you'll certainly end up being, you're not going to be on the front foot. So there are not everyone will win. So countries do have to think about where they're advantaged and take advantage of that if they can.
Thank you, Prof. The next question is from Dr. Ali from UKM. So based on your experience, you have worked with, there were 2 companies spun up from Imperial College, and you were heavily involved in founding them. So we would like to know how from your experience, how do you attract entrepreneurs and investors when it comes to hydrogen and fuel cell research?
Yeah, well, I'd say that I think anything to do with hydrogen is attracting a lot of investor interest at the moment, partly because the hydrogen stocks have gone up so quick. So the value of hydrogen-related businesses have rocketed in the last 18 months. So there's a lot of investor interest in hydrogen at the moment. I'd say that, of course, for a long time, there was almost no investor interest. So the situation has changed quite sharply in the last period of time. How do you attract it? So it's always hard, right? So I think investors are attracted by a couple of things. They're attracted by the team. So when you've got a new stage technology, an early technology, which really doesn't have any proof other than you can tell people how good it is, they back the people a lot. So the people's credibility matters enormously. I have the advantage now of having done a company that's now worth £2.5 billion. So people tend to listen to me. There's no reason my ideas are any better than anyone else's, but that track record counts. So having people, the people side's important. You've got to have an idea that is transformative, right? There's no point, no one will invest in something that's just a little bit better than something else, because there's a lot of risk to take along the journey. So you need a good idea. It needs to be robust. It needs to be defendable. You need a strong IP position, and you need a good team. And then you've got a chance. Happy to talk further about specifics, but let's call those a set of generic answers.
Okay, thank you, Prof. So there are a few more questions. Can we still go on? Are you
yeah, why don't if we could give it, say, another 10 minutes, and then I'll need to head off. Is that all right with you? 10 more minutes? So till 15:15 your time, yeah?
Okay.
Say.
So in that case, I'll give 2 more questions from the participants. So this one is from Mr. Tommy Hendertomo. Dear Prof, from 3 electrolyzer types, which one is the best to produce hydrogen? from your research experience based on conversion rate, process mechanism, and cost?
Well, you know, there are, as I said, there are, they all have advantages and disadvantages. Alkaline are the cheapest today. They're the most mature today. They are the lowest power density today. So you need a bigger piece of equipment to produce a given amount of hydrogen. Well suited to baseload applications. They don't load follow well. PEM are a rapidly emerging area, but they need platinum group metals and iridium. So that has a supply chain concern. They're more expensive than alkaline because they have more expensive materials and they're not made in such large volumes. But they produce hydrogen at pressure, which is useful for refueling applications in particular, and they can load follow. They both have similar efficiencies. Moving up, if you like, in interest, but still far behind the others in terms of maturity, is solid oxide, which has by far and away the highest efficiency. It has the advantage you can recuperate heat into those devices to further increase the efficiency. You can get close to 100% efficiency by recuperating heat into the device. But are somewhat unproven in terms of lifetime and are far less mature. So, and are likely to not be that flexible, but we don't know because we haven't built that many. There are a couple of emerging technologies that I didn't discuss. So Alkaline Pem, there are quite a lot of small startup companies now working on Alkaline Pem Electrolyzers. So this is a bit of a hybrid of an alkaline and a PEM. So it's PEM technology, it's membrane technology, but it doesn't use acid chemistries, it uses alkaline. Alkaline's much easier, you don't need platinum group, then you don't need platinum group metal catalysts. So it avoids the platinum and iridium issue. It also makes the oxygen reaction more facile, so lower power density. So those are interesting, but they're at this kind of startup stage. And there are some other startup type companies which use some very different concepts for water splitting, which effectively separate out where the reactions happen at the anode and cathode. They don't have a conventional electrolyzer design, which again promise much lower cost. So it's quite, I think the electrolyzer space is an area still with room for lots of innovation. I've got a question from Zada Jamil. I should answer Zada's question because Zada was a PhD student in my group a long time ago. Well, not that long ago, Zada. Can you read out? It was a question around fuel cells, but I only flashed up on my screen.
Right, okay.
Can you read out the question for me as well?
So that's a question from Zadariana Jamil. Hi, Prof. Since you're involved in both fuel cells and battery studies in hydrogen fuel cells versus batteries, which one is more economical and promising for the future?
Well, you know, I think it depends on the application. I mean, the first thing to say is that there's been huge progress on battery electric vehicles, right? And, you know, all mainstream manufacturers have battery electric options, ranging from pure battery through various types of hybrid. And that sort of footprint in the market, it gives them a huge advantage. For fuel cell electric to compete with those, you will need a widespread hydrogen refueling infrastructure. And I don't think we're going to get a widespread refueling infrastructure straight away because it's expensive. So I think battery electric is going to win out in the light duty. The only time that will shift is if we do get lower cost hydrogen coming through at scale, and then we can start to see it being promoted out. Because from a consumer's point of view, a hydrogen fuel cell electric vehicle is actually, provided that you can go and refuel it easily, is a fantastic choice. It's just like driving a battery electric vehicle, but it only takes 3 minutes to recharge it at the petrol station. So that's good, but you know, I think, but you know, all the advantages in all vehicle electrification carries advantages for all other types, right? The motors, cost down, the control systems, consumer acceptance of electric as a form of propulsion, maintenance, and so on. All of these things are benefited. Where hydrogen fuel cell electric is advantaged is in the heavier duty vehicles when we need a lot more energy on the vehicle, either because we want to go a long way in a long distance truck, or because it's a very heavy vehicle. Then batteries really struggle. So point-to-point use, heavy duty, where we don't need professionally maintained vehicles, I think where we'll start, like buses, trucks and things. And that's much clearer that hydrogen fuel cells are advantaged and worth starting with. Did you have another question you wanted to ask? One more perhaps? How are we doing? If I can give a quick answer.
Yeah, okay. We have, maybe we can make this the last question.
Sure.
Is that right? Okay. So the last question is from Dr. Nurasikin Amaluddin from UKM. What is the most efficient benefit or return in terms of producing hydrogen for power generation using renewable or directly use the electricity from the sources? And what is the potential of green hydrogen compared to storage of the energy in the battery?
Yeah, I mean, it's a very good question, right? And I mean, just to say a couple of things, right? One is, if you've made renewable electricity, the first thing we should do is use that electricity directly. Because if we're going to make it into hydrogen, we're going to suffer a cost and efficiency penalty. So if we can use the electricity directly, we should. If we can store the electricity in a battery, then rather than making hydrogen, provided it's something like a lithium-ion battery, you get about over 90% of the electricity back out again when you put it into a lithium-ion battery. If you're putting it into electrolyzers and then turning it back into power in a fuel cell, you know, you're going to be 50% round-trip efficiency. Now, it might still be the best thing to do, simply because we can't use the electricity locally, or we can't move it long distances, or the end use can't use the electricity, it needs a different energy carrier. But if we can use the electricity directly, that's the first thing we should do. If we can put it in a lithium-ion battery or a high-efficiency storage device, we should do so. And if we can't do that, we should turn it into hydrogen. And if we can't use the hydrogen, we might think about turning it into ammonia, because that's got another efficiency penalty and a cost. And if we, or into a synthetic e-fuel for aircraft, but again, that has a big efficiency penalty and a cost. So we need to think about these things, but we shouldn't rule out some of the other options like e-fuels and hydrogen, just because they're less efficient. They are, in many cases, the only way we can deliver the functionality we need, so that's what we should do. But neither should we rush to do it rather than keeping the electrons as electrons. So we try and minimize every energy conversion step because it adds cost and lowers efficiency, but not be hung up only on efficiency. It's not the only thing that matters. But it's a good question. And so the answer depends on the context and the system.
With that last question, that's the end of our Q&A session. Thank you so much, Prof. Nigel, for sharing your time, knowledge, and experiences with us. SELFUEL would also like to present an e-certificate of appreciation for our distinguished international professor, Dr. Nigel Brandon.
Thank you very much. Thank you.
Thank you very much, Prof. Nigel.
Okay, and I hope to see you all in Malaysia at some point soon and pick up on some of these questions. Okay, thanks everyone. Thanks, bye-bye.
Thank you, Professor. Bye.
We have come to the end of our event. Before we wrap up this webinar, I would like to thank Tan Sri Abdul Wahid, Chairman of the UKM Board of Directors, on behalf of SELFUEL for attending our session today. We really appreciate it. And thank you for the very good question. And we hope that Tan Sri Abdul Wahid will be able to give his time again for us in our future webinars. So. Okay, ready? 1, 2, 3, smile. Okay, smile. Smile. Okay. So, okay. Thank you very much, everyone. Thank you for attending today's webinar until the end. We welcome all participants to visit our website for more information on the Institute. If you have any other questions, please contact us through the details currently shown on your screen by scanning or saving the QR code.
Okay, thanks a lot. I'll dial off.
Thank you, Prof. Nigel. Thank you very much.
Nice to see you all.
On behalf of everyone from Institut SELFUEL, University Kebangsaan Malaysia, and our distinguished international speaker, thank you for joining us today and have a great day.